you see that the sum of the regions have a main chain clearly visible. This is at 3 angstrom. Now this is at 6.5 angstrom. At 6.5 angstrom, now you see that alpha helical or some cylindrical structure, more larger structure, and at 8 angstrom, now it's getting more like the smooth, and then detailed information is lost. And then at 16 angstrom, now you don't see the detail of atom at all. You just see the overall volume. Now, typically, the resolution you get is by experiment is usually at the very beginning between like 5 angstrom to maybe 8 angstrom. And then by trying to improve your samples or the conditions of cryo-EM, you will try to get the better resolution up to probably 3 angstrom or even better. But that is not always possible. So we apply, in our lab, we apply many AI-based methods, like, deep learning, to be able to get more information from the cryo-EM map of lower resolution, and then try to get the structure information from medium medium low to low resolution images. So I'll show you several tools we have developed, which is suitable for several different range of the resolutions. So, okay, I start from a lower resolution from 6 to 10 angstrom. At 6 to 10 angstrom, you see that this kind of images, you don't see the atom position at all, basically. But you see, you may be able to see some backbone directions. Okay, at this resolution, if you apply here, the methods we developed called EMAP to secondary structure, EMAP to SIC, which was featured in the cover image of the Nature methods at that time, applies the deep learning. It's an AI-based image processing methods to identify the secondary structures. So what this method does is, okay, you have a cryo-EM map at this low resolution, and then this method will scan this map with a box. The size of the box is 11 by 11 by 11 angstrom, and then at each position of this box, by using the deep learning methods, it will detect if the box include alpha helix, beta strand, or coil. So from a computer science point of view or software point of view, this is the classification to 3 classes. So this will predict if a box have either alpha helix shown in red or beta strand in yellow or coil. I skipped the neural network part. So new architecture of neural network is called convolutional neural network. This is a very classical convolutional neural network. And this is some example of the the output by EMAP to SIC. So okay, you see that the several panels, but maybe I can look at explain the panel C. Panel C is a proteasome. On the left shown is the structure in a map. So you see that the red region is alpha helices and yellow are beta strands. So this is taken from the database, PDB, and also the EMDB. On the right is the results of this deep learning. So the yellow dots are predicting that this position include beta strand, and then red dots means that this position is predicted to have alpha helices. As you can see visually, they agree relatively well to each other. And then rest of them are the same type of examples. And then these examples are from maps of 6 angstrom to to 9.1 angstrom. So even at the resolution of 9.1 angstrom, 9 angstrom is really low resolution. By eyes, you don't see much. But by applying the deep learning, you can still see where the beta strand and alpha helix is located. This is accuracy, general accuracy. So we tried, well, in the paper, we tested the methods in two types of data set. One is on simulated, computational simulated map, which is very clean, but I explained that the results on the experimental map. So here, x-axis is a map resolution, y-axis is accuracy. When the map resolution is around 8 angstrom, so 5 to 6, 5 to 7 angstrom, the accuracy is reaching around 80% or 70%. So even this method is relatively robust. Even when the resolution is even worse than 8 to 10 angstrom, most of the cases, the accuracy of the classification is still about 60%. At 9 angstrom to 10 angstrom, when it is very difficult to see anything by eyes, some maps are not performing very well, but there are still several maps which can achieve close to 80% accuracy. So especially when the map resolution is low, from 7 to 10 angstrom, these results is much better than what you can see by eyes. So the EMAP2-seq previous method is only for detecting proteins, but you can also detect DNA or RNAs in the CryoEM map. So this method now the updated version of the EMAP2-seq, which is called EMAP2-seq Plus. This method will also detect the DNA or RNA in the map. So the idea is the same, although the detail of the neural network, deep learning is a bit different, more advanced. But the idea is the same. So here you have the CryoEM map of 5 to 10 angstrom, where it is very difficult to see anything by eyes. This method will scan this map by the box, and then at each box position, it will predict if a box include either alpha helix in red, beta strand shown in yellow, or coil in green, or DNA or RNA. So now it is full-class classification. At each position of the box, it predicts it is alpha helix, beta strand coil, or DNA or RNA. And in terms of the architecture of the neural network, if you are interested, it is using the convolutional neural network called ResNet. So ResNet is a bit advanced architecture in deep learning. So this is again some examples here. For example, A is the nucleosome. So in the nucleosome, as you may know, there's a proteins in the core, and then DNA is wrapping around. And this panel A is, resolution is 5.1 angstrom. And at this resolution, you can clearly see the alpha helix and coil and the DNA very clearly detected by deep learning. You can and so on. So here in this C is helicase. Helicase is a protein which have the DNA in the middle of this complex, and then as you see that DNA is very clearly detected. Even the pitch is also clearly detected, and alpha helix is also very clearly visible. So this is what the deep learning can do when the resolution is from 5 to around 10 angstrom. Here, this is the accuracy of from the experimental map. So I explained A and C. A is showing the accuracy on the y-axis for the maps of resolution from 5 to 10 angstrom. And the red dots are showing the overall accuracy. So when the map overall accuracy of full class classification, alpha helix, beta strand, coil, or DNA RNA. So when the resolution is up to 7 angstrom, most of the cases accuracy is about 80%. When it goes to 8 to 10 angstrom, accuracy is dropping around 50%. But by eyes, you don't really see anything for the resolution of 8 to 10 angstrom. The blue is only showing the accuracy of DNA and RNA. For DNA and RNA, the accuracy stays almost close to 100%, 90 to 100%, even for the resolution of up to 10 angstrom. C is showing the two-class classification. In C, I made the problem a little bit easier. So here, the purpose is just to distinguish protein region or DNA RNA. So it's a two-class classification. The DNA and RNA accuracy is basically same as in panel A. So even at the resolution of close to 10 angstrom, well, in about half of the cases, the accuracy of detecting DNA RNA is close to 90%, 80 or 100%. For proteins are also very stable, predicted very stably all the way up to 5 to 10 angstrom. So the classification of protein and the DNA RNA is relatively easy by deep learning. So now I explain a couple of methods we developed for the building the 3D molecules from the CryoEM map. Now, and for comparison, the recent methods we developed uses deep learning, but for comparison, first I explain our methods developed in 2018 called MainMust. What MainMust, and then later we apply deep learning to the similar ideas of MainMust. So this is a baseline. This MainMust is for building the structure from the map up to around 5 angstrom. When the resolution is worse than 5 angstrom, 5 to 10 angstrom, the atomic structure modeling is getting more difficult. So the target of MainMust is the resolution from 5 angstrom or better, right? So I just wanted to show you that the idea of the structure building is a very intuitive and straightforward. All right, so here you have a CryoEM map, and then the first step is to identify the positions in the CryoEM map which have high enough density. Because in the CryoEM map, the map data, the positions which is in high density, which have the high density values, is where the atom locates. So first we identify the points in the CryoEM map which have certain density value or higher. Then, okay, so those dots are showing the positions with high density values. Now we cluster it. We do the local clustering step by step, and then to identify the representative points for of the high density regions. Then after that, we connect those dots into by edges, by lines, which now look like this. So here, so the each dot corresponds to the place where the density is very high, and then those lines are connecting those high density regions. If I remove those dots, now it looks like this. So if you are familiar with the protein structure, you already started to see some protein-like structures. For example, here, these are the alpha helices. So this is corresponding the beta strand, and then loop, turn, and then beta strand. So you see already the protein structures, but now but those are all connected into a graph, and we need to identify where the protein chain starts and where the protein chain ends. For that, well, it turns out that by using by detecting the longest path between in the graph, most of the time corresponds to the protein chains. So from this graph, the idea is to identify the two ends of this graph, which makes the long path, and then we generate lots of different structures. And then after making lots of structures, we map the sequence to the structures, and then find that the structures which fits to the protein sequence the best. So that's the ideas of the main must. But now, very recently, actually, this week, our new method was published in Nature Methods. Again, this was features in the cover of this Nature Methods of the January issue. Now we apply the deep learning to this main must protocol. So previously, we have first we identify the high dense points as the candidates of atom positions, but now we apply deep learning. So first, okay, so here we have a CryoEM map of up to about 5 angstrom, and then now we detect where amino acids and the atom locates by deep learning. So deep learning architecture we apply is now called UNet. This is another type of deep learning methods, but this deep learning methods will identify where the C alpha, nitrogen, and the oxygen in the main chain locates in the CryoEM map. Deep learning can also tell the amino acid type of C alpha positions. So now using this predicted amino acid type and the atom position, and then we connect those detected amino acid positions to make the entire structure. So, okay, so we first connect those dots to make the fragment of structures. For that, we are using the methods called vehicle routing problem. This is a method to connect the dots, identify the C alpha positions if they are close enough, and if they look like the protein chain. Now, then after we identify the fragment of structures, then we map the sequence. We can do this because the deep learning can tell amino acid types at each positions. Now, then up to here, we have the fragment of protein sequence, protein structure, and the sequence, and then we want to combine them. That is done by the mathematical methods called constraints program solver. But this is a very intuitive, because after you identify amino acid types and atom positions, even manually, you would want to connect those dots together to make the fragment, and then assign the sequence, and then connect everything together to build the entire structures. But here, we also consider, so another thing we considered is the protein 3D structure prediction. You might have heard about AlphaFold. AlphaFold is the protein 3D structure prediction methods using the deep learning. And recently, the AlphaFold is doing very well in structure prediction, and many structural biologists are using it for when they want to interpret the X-ray data or cryo-EM data. By now so first they can do the structure prediction and then fit the structure into the map. So we also consider the AlphaFold structure prediction, but the important thing is that AlphaFold structure is not always correct. So we don't use the AlphaFold structure as they are. but basically the idea is only to use local structures from AlphaFold model, which fits very well to the traced density. So now we have two sources of the information of the structures. One is coming from this by tracing the the CryoEM map, and another type of information is coming from the structure prediction. Now we combine these two information, traced structure fragment, and then the predicted model from AlphaFold together, and then combine those fragments together, and then using that fragment, we build up the entire structure. This is some just one detailed information about when the two fragments are connected. So suppose in the CryoEM map, we have traced two fragments. One is in green. Suppose here I have the fragments which have the amino acid assigned from residue amino acid position 1, 2, 3, 4. And then suppose we have another fragment in the CryoEM map which have the amino acid assignment of amino acid 7, 8, and 9. And well, although these two fragments, so during the tracing, we have lots of fragments. So here we have about typically for a CryoEM map, we have about 1,000 to 50,000 fragments. And then we want some of the fragments are not correct, and some of them are correct. So that we need to find the correct combination of the fragments. And this is here, if I have two fragments like this, I don't connect these two fragments because the residue 3 and 9 are too close for a protein. If amino acid residues are close, but they should not be too close to each other. And there are appropriate distance for residues pairs depending on the amino acid positions. So the second example is situation where two fragments 1, 2, 3, 4 and 4, 5, 6 are close in space. But here the situation is that this position is assigned residue 4, and then this position slightly, which is farther than 3.5 angstrom, also assigned with the residue number 4. If the distances are too far away, we don't connect it. But if the identified residues 4 and 3 in this example are close enough, then we combine them. Yeah, this is another example. If I have these two fragments, in this situation on the left, I don't connect it because 4 and 5 are too far away. But if 4 and 5 is less than 5 angstrom, we will connect it. So although this deep main-mast has several steps, what I wanted to tell you is that this is very intuitive. This is very similar to what you will do. You will model the structure by using COOT or some interactive software. We are doing the manual steps by programs, but each step is interpretable and very easy to, it's mimicking how you would do modeling by hand. So, okay, so this is some example of deep main-mast results, and in comparison of AlphaFold, as AlphaFold 2. AlphaFold is a structure prediction method which does very well in general, but there are typical cases when AlphaFold model does not agree, is not correct for a CryoEM map. The first example is a protein structure which have two domains. So as you see that this protein have alpha helical domain and beta domain, AlphaFold structure prediction can do that structure modeling very well for two domains individually, but often the relative orientation of the two domains is not correct. But the deep main-mast, since deep main-mast is tracing the CryoEM map directly from the density, it can do that tracing very well. So here I'm showing two examples, two results, deep main-must base and deep main-must. Deep main-must base is not using AlphaFold at all. This is results is coming from just direct tracing. RMSD is 0.57, very good. TM score, this is another score of structure modeling, which is, and the 1 is perfect. So in this model, 0.99 is close to perfect modeling. Deep main-must here is a combination of the full pipeline of deep main-must, which uses tracing from deep main-must and then AlphaFold 2 models. So in this case, since tracing is already very good, adding AlphaFold does not make much improvement, just RMSD improved from 0.57 to 0.52. This is another example. This structure has a very long beta strand tail. If you use AlphaFold, actually, these tail regions are not very well predicted. If we compute the RMSD value, the RMSD is very bad, 35.3 angstrom. So some local structures are correct, but this long tail is not predicted by AlphaFold. But deep main-must is tracing the positions, beta strand, so it can do the structure, the model building for this long beta structure tail very well. And RMSD is 4 angstrom, and combining the tracing with AlphaFold is recovering the structure also very well. Okay, RMSD went slightly worse, but the TM score went slightly up from 994 to 95. So here, okay, and this is overall comparison between deep main-must and then AlphaFold. So here, this is tested on 178 CryoEM maps. The x-axis is a TM score of AlphaFold, and then y-axis is the tracing part of the deep main-must. It's called deep main-must base. So in this y-axis, AlphaFold model is not integrated. When we compare AlphaFold modeling with our tracing methods, so for out of 178 maps, 91 cases the tracing did better, and 87 cases AlphaFold did better. But you see that the number of times we win and loses against AlphaFold is almost similar. But if we now combine our tracing methods with AlphaFold, it's a now full deep main-must, then we can clearly win over AlphaFold 2. Okay, so here is some examples. So this is this is a 3-chain complex, and this is a 14-chain complex. It's very difficult even try to well, if you try to build a model by hand, this is not trivial. This is not easy, but deep main-must can do almost perfect modeling. This is fully automated without no manual modification. So all right. So I have a couple of more topics here. This is so during the course of the development of deep main-must, we noticed that since the structure modeling of from CryoEM Map is not easy, well, even the published protein structures made available in PDB and EMDB are often not correct. So so DAQ score, this is a deep learning based amino acid residue-wise quality assessment score. This is to find out to evaluate if a protein model existing protein model is correct. Idea is very simple. So you have a now CryoEM map, and then now you also the input is also the PDB structure you want to evaluate. And then we apply basically the same deep learning methods which detect the amino acid type and atom positions, and also the secondary structure types, and then checks if the model agrees with deep learning prediction or not. If the deep learning prediction disagree with the model for consecutive positions, then it's highly likely that the model is incorrect. So yeah, so I skip the detail, but idea is the same. We train the deep neural network on the data set of experimentally determined cryo-EM maps of up to 5 angstrom. And then this is some example. This is an example where the DAQ score detected actually incorrect regions. I skipped this a couple of slides of DAQ, but the DAQ is application of the deep learning part of the deep mainmast. So yeah, we also compared against the existing methods, but when it comes to so there are several scores which try to evaluate or which try to evaluate the structure quality, model quality of the known, the existing structure models. But when it comes to detecting the wrong positions, our DAQ performs much better than existing methods. We also applied our DAQ score against the entire PDB structures. And this you can access this DAQ score database, daqdb.kiharalab.org. And here we have analyzed the over 170,000 protein structure chains determined by CryoEM and then now available at PDB. So in a long story short, about 15, okay, I skipped this, but about 10 to 15% of the protein structures in PDB seems to have errors in it. This is okay. This is some example of detected errors. So okay, I explained this first panel, and then last panel. In the first panel, okay, so the DAQ score complained that the middle part of the structure, and the structure looked like this. So the model is fitted into the density, but as you see that some of the side chains, like this phenylalanine 9, is exposed outside of the density. But if you shift the sequence, if you run AlphaFold to make the model, actually the AlphaFold model shift the sequence along this density. So now proline 11 goes to this position, and then phenylalanine 9 goes to this position, and then that makes the structure fits much better to the density. And the DAQ score can detect this kind of sequence shifting errors. DAQ also identified very extreme cases like this. In this structure, actually, the chains are almost entangled, and you can see that this is not possible for a protein structure. And the important thing is that there are this kind of structures in PDB. So you cannot trust the structures in PDB 100%, and you need to be a bit careful, especially when the structure is determined, modeled from the lower resolution CryoEM maps. All right, so another tool we have developed is to fix the errors of protein models. So previously in the previous slides, I show you the DAQ can identify the wrong regions in the model. Then question is how to fix it. Now DAQ Refine is the tools to fix the errors detected by the DAQ score. So what it does is, okay, so first you have the model, protein structure model with CryoEM map. and then DAQ will identify positions which may be wrong. Now, what DAQ refine does is it uses AlphaFold structure prediction methods, but in a very specific way, so that AlphaFold only makes corrections to the wrong regions, instead of allowing AlphaFold to build the entire structure. So we will show you that we have website for this too. Now the the CryoRead. Okay, so now I switch the topic to DNA RNA structure modeling. So deep main must was to build the protein structures. CryoRead is using basically the very similar technique, but it is now building the DNA RNA structures from CryoEM map of up to about 5 angstrom. Idea is very similar. You have a CryoEM map, and then deep learning can detect the position of sugar. Sugar position is here, ribose structure. So deep learning will detect where the ribose locate, and then where the phosphate locates in the main chain of RNA or DNA, and then where the base locates. And now, after identifying those key positions, phosphate, sugar, and base position, we use basically the same pipeline to connect those identified positions, and then assign the sequence, DNA or RNA sequence, and then connect them to build up the full model. Yeah, so this is accuracy of the model. So I'll just show you, discuss this two panels. So on the left, this is the y-axis is basically the accuracy of the percentage of the nucleotide positions, which are correctly modeled, and then x-axis is a resolution. So resolution is we tried is up to 5 angstrom, and when it comes to the structure modeling, without considering the sequence assignment accuracy, actually the structure modeling can perform very well up to even at 5 angstrom, accuracy is about 80% or higher. On the right is shown is the now backbone accuracy, which is same as on the left. But also I'm showing the sequence assignment accuracy. Sequence assignment means that here I wanted to assign the ACGT at its correct positions. That is okay. So when the resolution is relatively low, 4.5 to 5 angstrom, identifying the base types correctly is getting a little bit difficult, so that the accuracy started to decrease relative to the resolution. When the resolution is around 3 angstrom to 3.5 angstrom, sequence assignment accuracy is about 60%, and then it drops a little bit when it goes to around 5 angstrom. This is some examples. So here, this is DNA RNA structures. In this case, this is a DNA structures in the CryoEM map, and then this is a model built automatically by CryoRead. This is the RNA structure. This is this is just a part of the CryoEM map, but the CryoRead can identify the position of the nucleotides, nucleic acids, and then build the structure in the correct positions. We can also build very large structure. This is the ribosome. All right. So I have just 3 more slides. So this is our very recent development for modeling for maps of 5 angstrom to 15 angstrom. So I mentioned that the deep main mass for proteins and CryoRead for DNA RNA is for maps up to 5 angstrom. And but now using now recent methods, machine learning methods, deep learning methods called diffusion model, we can do the modeling even for lower resolution maps of up to around 15 angstrom. Diffusion model is a deep learning methods in the category of generative models, and then it is a method which is used in DALL-E or Midjourney, which makes artificial images. We can use such diffusion model also to sharpen the image of the CryoEM map. Well, this is the general introduction of diffusion model. What diffusion model wants to do is that diffusion model is trying to learn the pattern of how the sharpened image is degraded to the noisy image. And by reversing the process, we can make a noisy image into a much sharper image. So this is some examples. So by using the diffusion model, we can sharpen we can generate the sharpened image of the CryoEM map for the map in this example for 7.5 angstrom. And then, well, this map is actually it's a bit difficult to see, but has more clearer information of alpha helices and then how main chain goes. And by using this sharpened image, we can fit the structure much better. So here, this is, okay, so the name of the tool is diff modeler, or okay, at that time we called it diff EM fit. But what it does is that, okay, so you have a CryoEM map of 5 to 15 angstrom, which is very difficult to model. And then first we apply the diffusion model to sharpen the image. By sharpen the image, so it now gets very easy to much easier to fit the structures. Often the structure to fit is not available, but here we use AlphaFold to build the AlphaFold models, predicted models, and then now we fit this predicted structure to the diffused map. And then this process is getting much easier because the CryoEM map is now more sharpened. And by using this method, we can build very large structures. Like this case, this is the ground truth structure, and this is the results of this diff modeler, our new tool. Although there are some structures which are not correctly placed, but most of the subunits are correctly placed in this map. All right, that's all. So I introduced several methods, and all these methods are available at our lab website. Please search probably my name and then also the CryoEM, and then you will find this website, EM Suite. EM Suite include many tools for map structure analysis, and then also the DAQ database and the modeling tools, including deep main mass, CryoRead, and then DAQ Refine. And for major the tools also have the web server. So web server does not really does not need any installation of the software. You can just upload the CryoEM map and then protein sequence or DNA RNA sequence information, and the web server do the modeling for you. From the EM Suite, you can download the source code and then install it on the lab computer, and then you run it. So, okay, quick summary. So we have a DAQ score, which can check how the structure, if the structure is correct. And then we have the structure modeling tools, deep main mass and CryoRead for protein and DNA, RNA. If you have, please try the web servers. And then good thing about this web server is that you can try it by using the data which you can download from EMDB and PDB. If you have any questions, when you try it, feel free to contact us. We are very happy to help. All right, so this is the last slide I have. This is done by my entire research group, and especially Dr. Genki Terashi, who is going to talk next, and then Dr. Shao Wang, and then Dr. Tsukasa Nakamura. He is another researcher, PhD researcher who developed a database. Okay, thank you very much. That's my part of the presentation. Now I pass the presentation to, I think, Dr. Genki Terashi. So I stop sharing my slides. Thank you.
All right. Once again, we want to appreciate you, Professor Kihara, for your inputs, the knowledge you've passed. We are really grateful. So we're waiting for the next person to come on board.
Dr. Kihara, is
Yes.
Wang or Genki continuing? Who is going first? Who among them is
now
going
again.
first? Okay.
Hello everyone, can you hear my voice?
Yes, very clearly.
Okay. Okay. Hi everyone, my name is Genki Terashi. I'm an assistant research scientist in Kihara laboratories. So I'm a member of the developing teams. So in these sessions, I will explain the two programs. So first is the DeepMap, the protein structure modeling program. And also I will show the model assessment program, the DAQ scores. So we provide this program on the web server platform and Google Cloud platform. And I will explain how to use these programs. So it's very easy to use. So if you have a EM density map data and protein sequence, please try to use a DeepMap. And also if you have a protein structure models and EM density map, you can estimate the accuracy of the atomic models by using the DAQ scores. So later, maybe we will provide this presentation files to the audience. So there's some links like this. So you can just click these links, then you can visit our web server directly, and also you can check the result and see how it looks like. Okay, so to start my presentation, as Professor Kihara said, we released the Kihara Lab EM Suite server. So this is a new server. Last year, we released these web servers. So from this web server, you can use our latest programs. Very easy, it's free. And also, we provide the GPU computation in the backend. If you don't have a high-end GPU machine, don't worry, because our web server provides a computational power. So just clicking these icons, if you want to build a protein structure, just click the deep main math. And also you can try the DNA RNA modeling and scoring and so on. So please later visit this Kihara.org website. It's very easy to use. So in this website, so it has a very nice feature. It's a registration. So you can make your account in our website. So by registering your names and email, so you can keep your record, your modeling result in the server. So that means that later you can check all jobs and then check the result. And also that you can get some notifications once the computation is done. You will get the notification, so you don't have to wait for the 2 or 3 hours on the browser. So once you submit a job, then you will get notification. This is a very nice feature. So if you want to use a web server, please try to register your account. But of course, you don't have to. So this is optional. You just want to try some features in our web server, please just try to use it. It is optional, but it's very useful feature in our website. Okay. Okay, let's start the deep main math. How to use a deep main math? Yeah, as I said, deep main math program is available on the 3 platforms. So first is the web server, second is the Google Cloud, and third is the source code, install code from GitHub. So these 3 platforms have different advantages. For example, in the web server, of course, you don't have to install the programs, so because the programs are already installed in the web server. But you need to upload your density map to the server. So that means that it's not perfectly confidential. So because the server administrators, so like we can check your data. About the hardware point of view, so we provide 8 CPU cores, and GPU memory space is 24 GBs. It's relatively large. Then also the computational time limit, there's no limit. So you can submit as many as possible. So it's unlimited. Then also the deep math can build the full auto modeling and refinement. So this part are done by the Rosetta program package. So you can get the full atom cell chain structure, full atom protein structure. Then, and after computing, you will get the 4 full atom models, up to 4 full atom models. So this is a web server. The second platform is the Google Cloud platform. So Google Cloud platform is a free Jupyter notebook style platforms. So these computational resources are provided by the Google. So installing it's very easy. So you just click the few buttons, then it automatically install the program on the Google Cloud platform. Then of course this is confidential. So only user can see your results. But hardware point of view, it has only 2 CPU cores, so it's much slower than the web server. And also there's a limitation of the GPU memory space. It has only 15 GB. The another limitation is that it's a free platform, but you can use this Google Cloud platform deep math program up to 4 hours. So that means if you want to build a relatively large protein structure over 1,000 2,000 amino acid residues. So it's not enough computational time. So because of the limitation of the computational time, this Google Cloud Platform Deep Math can build only C alpha positions, C alpha modeling. Then third platform is installing the entire code from the GitHub. Well, this is the most straightforward way. So you need to download the source code from the GitHub. Then you need to install the Deep Math program on your machine, on your PC. So you need to set up the Python conda environment. And of course, you need to set the GPU card because Deep Math uses a GPU. Of course, it's confidential. Then you can set up as many as possible CPU cores if you have. And also you can use a large GPU card. So the minimum requirement of Deep Math is it should have over 8 CPU cores, and GPU should have a larger than 10 GB memory space. So because the program are installed in your computer, so it's unlimited, of course, and also you can use the full atom protein structure modeling. So you can control the full parameters. So if you want to generate more structures, so you can generate up to 20 full atom models. So there are 3 platforms. Okay. Okay, let's move to the how to use the Deep Math in web servers. As I said, all programs are provided in this website. So this server has a 24 GPU memory space, then 8 core CPUs, then there's no CPU time limitations. Then it can perform the full atom model building, the refinement part. So this is the top page of the web server. So please click the Deep Math. So these presentation files contain some links. So this is some examples of the output files. So later you can check the result. Okay, I will show how to use this Deep Math web servers. So this is a job submission page. So first, you can put the control levels. So because the density map, you can change the shape of the density map by using the control levels. So if you don't know the good control levels, you can put the 0 values. But if you use the sufficient control levels, it looks like the more protein shape like control level, then you can reduce the computation time dramatically. Then here you can submit your density map, EM map. Then also you need to upload the sequence file here. So sequence file should be the FASTA format file. So like this kind of format. Chain A is an amino acid sequence like this. Then chain B is this. Then chain C like this. Then please upload the FASTA file. Then here are some options. So as Professor Kihara explained that the Deep Math full pipeline can use the AlphaFold2 models. So if you have AlphaFold2 models for this density map, you can upload the AlphaFold2 model. This is optional. If you don't have AlphaFold2 models, you don't have to. But if you have, you can upload the AlphaFold2 structures. Then there are some other features. So this is the homo-oligomer chain assignment. So one of the new feature in Deep Math is that if the density map contains the homo-oligomer protein structures, so Deep Math can define the chain ID assignment. So if you know that this density map have a homolygous protein structure, please turn on. And this is another option, is the full atom model building. So this option is using the Rosetta full atom construction part. So it will build the side chain and also fit to the density map, define the full atom structure. But this computation is takes a relatively long time. So especially if you are computing over 2,000, 3,000, 4,000 amino acid residues, so these full atom constructions and refinement will take 1 or 2 days. So if you just want to see the backbone tracing structure, you don't have to turn on. But if you want to build the full atom structure, please turn on this option. Once you set up the all options, you just click upload. Then server starts the computing, deep memory computing. So this is the examples of the deep memory modelings. So these results are shown on the web servers. So here is the links. You can check the output files. So this is a 3.8 angstrom. So this gray shape showing that density map. From this density map, deep memory can build the protein structure. So this blue lines showing that's the backbone structure in this density map. So this model 1 only showing that the C alpha model. The model 2 show the very confident regions. So because EM density map, some regions have a relatively locally low resolution, so our quality is not enough to build a structure. So in such case, deep memories can build a structure, but it's not confident. So this model 2 is showing the very confident, high confident regions. So then model 3 is showing the full atom structures. So full atom structure, it has a side chains and all chains, all atom positions. Again, so these structures are showing the entire full atom structure, but also it shows some colors. So these colors are correspond to the DAQ score, Professor Kihara said. So DAQ score tell us the pitch position is accurate, very confident. The pitch positions are low confident. So here, low confidence regions are colored by red. So these loop regions, so deep memory is not confident, but it's built. The blue region is a high confidence region, high DAQ score. It's very confident region. The model 4 showing the full atom structure only confident region. Okay, so I've showed how to use this web server. On my browser. It's demonstrating. Okay, this is our website. Then, yeah, currently we are releasing these lot of different programs. So EMAP to SIG, EMAP to SF, the professor presented, and also DAQ scores are available, and CryoEM DNA RNA structure modeling programs are available. So now, yeah, we want to try the deep memory. So yeah, please click here. Then this is a job submission page. So here, this blue button showing that the very details how to prepare the input file and how to interpret the result. So there, the instruction. Okay, let's try to submit the job. So here, I simply select the some control level 0.1, then choose the EM density map. So click choose file. Then you can select the density map. For example, here, okay, I will try to submit this 2513 density map. Then open. And next is the FASTA format file, sequence file, choose file. Then I already prepared this sequence file. Select this sequence file, then open. So for this target, I don't want to, I don't have an AlphaFold model, so I don't select. Then this is not homologous. Then I want to see the result very quickly, so I don't turn off this Rosetta. Then just click upload. Then now job is starting in the background, so job is running now. Then after a few minutes or a few hours, so you will get the result. So in this website, so there's some job manager page. Then my jobs. You can see your own jobs. So now I submit these jobs. So deep math is running. So once you get the notification from the server, you can check your job results. So I can show some results. For example, here, click view buttons. So this is a result of the modeling results. So this target, this density map have a 3 chain. So this is 3D visualizations. Here you can see the results. So here are another examples. So 3 chain structure. So this is the density map. This is the result page. So you can see the structure. This is model 4, the full atom structure. If we want to see only the backbone structure, so here's the backbone structure. And full atom structure. So it's very easy to see the result and the density map. Okay, so this is the deep math web server. Okay, let's move on to the Google Cloud version. So deep math is also provided in the Google Cloud version. So Google Cloud version is available in this GitHub page. So this GitHub page also provides the entire source code. So in this page, okay, so there's a link, the Google Cloud. You can just click this link. Then you can go to the Google Cloud platform. It's a Jupyter Notebook style program. But again, I should mention that it's a free and confidential, but it has a 4-hour limitations. And also CPU power is only 2 CPU cores, and it has 15 GB memory space on GPUs. So maybe if you want to build a relatively large structure, this platform is not sufficient. But if you want to quickly build the structures for the small density map, please try to use the Google Cloud version. Okay. So once you click this link, this notebook link, first you need to connect the GPU card. So this is the notebook. Then click this link, connect GPU. Then you can set up the job name, then upload your density map here. So this notebook have numbers, and each blocks you just follow this cell blocks, then we can build the protein structure from the DeepMap Google Cloud version. So upload the map file, then upload the sequence file. It's very similar with the server. So sequence file should contain this kind of the FASTA format file. Then if you have AlphaFold models, please check buttons. Then this cell automatically asks you please upload your AlphaFold models. Then once computation is done, it will show the C-alpha protein structure models. So I use the same 3-chain target structures. So it also shows the low confidence regions and high confidence regions using the DAQ score. So, but it can only predict the C-alpha positions, so it looks like this. So if we want to build a flattom structure, we try to use our web server. Then third platform is the source code. So we are providing the entire source code of the DeepMap. If you have a GPU card, and also if you have a relatively high-end CPU, then you can install the DeepMap on your computer cluster. So please visit this GitHub page. This page contains the entire instructions and how to install the package and setting of the Python environment. Okay, so the next part is the DAQ score. DAQ score, this is the model evaluation. If you have a protein structure and if you have a density map, then you can estimate the accuracy, local accuracy of the protein structure model. So for DAQ score, we are also providing three platforms: web server, Google Cloud, and source code. So because the DAQ score is relatively fast and easy to compute, so you can select either of the platform. But the web server have some advantage. So because you don't have to install the source code, and also this web server can visualize the protein structures with the DAQ scores, and also you can check the 2D graph. So which position is accurate or which position is not accurate based on the DAQ scores. It's very easy to use. So we recommend to use the web server. Okay. So this is the top page of the web server. Then structure validations, proteins. So here there's a link for the DAQ score. Please click this link. Then this is a job submission page. It's very simple. You just need to upload the protein structure files and density map. That's it. Then once you put these two information, then please click this upload button. It will automatically compute the DAQ score. So I used one example. So this is the EMD 31563. So this is the COVID-19 spike protein. It's a relatively new protein structure. The result is here. So you can check the result. Okay, so this is demonstration time. So I've showed how to use this web server. Okay, so this is the web server. Then here you can see the DAQ score icon. Yeah, please click here. Then this is a job submission page. Then please select the PDB file you want to check. Okay, so I have examples. So 7FET, then open. In this case, I want to use this 31563 density map. Just select this one, then open. Then upload. So it's now uploading the density map and protein structure. Okay, so actually, I already computed the result. So here is the result. So this is the output of the DAQ score. So it looks like the homotrimer structure, 3 chains. Then here you can check which position is accurate or not accurate based on the DAQ score. So here, chain B and chain C and chain A are plotted. So it looks that these positions have a significantly low DAQ scores. So based on the DAQ score, if the DAQ score is lower than negative 0.5, especially these regions, it's highly possible that this position is not accurate. So here, there are 3D structures. So you can see that this beta seat region, this beta hairpin structure, DAQ score said this is highly possible that long sequence assignment modeling is not accurate. So this is very useful. So because based on these protein structures, maybe later some scientists want to build new drugs or analysis further. But if the atomic model is not accurate, this is critical for the further research. So estimating the accuracy of the protein structure is very important. Okay. Okay, let's back to the slide. Okay, as I showed that presented, this server is very easy and very easy to see the result. And also that we also provide a Google Cloud platforms. So source code is available here, GitHub, Kihara DAQs. There's a link for the Google Cloud platform. It's a free platform and also the confidential. So click this link. Then basically, you just open the cloud. You just need to do the almost same things in the servers. So in this page, in this notebook, you just click the runtime, this toolbar, then run all. Then this notebook automatically asks you to please upload your map or please upload your PDB file. Then compute very automatically. Runtime, run all. Then this block upload the PDB file, protein structure file here. Then next block, please upload your map file. It's fully automated, right? Then you will get the same result on the server. So notebook can visualize a 3D structure on the browser. Also, you can check the individual chains, which positions have a low DAQ score. and pitch positions have high DAQ scores. So 3D structures are colored by DAQ score. So high DAQ score correspond to the blue region. Then low DAQ score is colored by red. So after you computed the DAQ score, you can download the result file. So result file is archived in the input underbar evalue.zip file. So this file contains the 3 result files: DAQ score chain A, DAQ score chain B, and DAQ score chain C. Then you can manually check the individual positions by using the PyMo. So PyMo is a molecular viewer. So you can open these 3 files. Then please type the command spectrum B, red, white, blue, O, -1, gamma 1. Then the coloring is based on the DAQ score. Okay, that's it. So this is the summary and the references. So if you are interested in algorithm, so please check the papers. So Deep Math is a protein structure modeling program. So paper is published this January, and also source code is available here. The server is available. This link. The DAQ score is also published in the Nature method. So if you are interested in the algorithm, so please check this paper. The source code is also available in the GitHub page. And this GitHub page, this is typo. This should be Deep Math. So DAQ score and Deep Math is also available in the Google Cloud platform. So please visit the GitHub page. Now, of course, the server is available. Server it has a very powerful CPU and GPU card. You don't have to install the environment. So please try to use this link. Thank you for your attention. So please leave your comments or questions in the chat box. So then I answer any question. Thank you.
Thank you so much, Dr. Genki. Thank you for the information you just gave to us. Quite handy. So Dr. Genki Terashi has been working in the field of computational protein structure modeling for over two decades. His research experiences in protein structure modeling formed the foundational basis for his recent research projects. So he has applied advanced computer science techniques to his recent projects, such as the protein and nucleotide structure model for CryoEM maps, protein structure model evaluation for CryoEM maps, and protein docking, structure prediction, and structure database search. Now, through these projects, Dr. Terashi has gained valuable professional skills in both computational biology as a scientific researcher and as a software developer. In each of these projects, he has been the primary developer or a key member of the research team, actively contributing to programming and software development. As a result of collaborative efforts, Dr. Terashi has been able to publish research papers in high-impact journals as the author. He has extensive experience in developing and integrating computer programs across various fields of computational structural biology. So I want to thank you once again, Doctor, for your time and for your input. Are there questions or comments for Dr. Genki from the audience or from the online participants? Questions, please. All right, so in the absence of any other question, we want to appreciate you once again, Dr. Genki, for your time and for the information you have passed across. We're grateful. Thank you so much. So, back to the next speaker. The next speaker is Dr. Wang, who is now a postdoc at the University of Washington, Seattle, USA. He received his PhD degree from the Department of Computer Science, Purdue University, from the Department of Computer Science, Purdue University West Lafayette in US in 2023, and a BSc degree from Department of Computer Science in Xi'an, University of Xi'an, China in 2018. He is the associate editor of IEEE Transactions on Intelligent Vehicles. He has published numerous papers in a broad range of venues: Nature Methods, Nature Communications, and IEEE TPAMI. His research interests include deep learning, computer vision, bioinformatics, and intelligent systems. Especially his recent projects for protein, DNA, RNA structure modeling and evaluation for CryoEM maps have been widely recognized and used by the structural biology community. So at this point in time, I want to welcome Dr. Wang. Sir, the floor is all yours. Thank you.
Thank you. Can everyone hear me clearly?
Yeah, very clear.
Okay,
Yes.
great. I will begin my presentation. Thank you for coming to today our presentation. Today, my presentation will regarding two tools developed by me, CryoRead and Diff Modeler. So in short, CryoRead and Diff Modeler focus on two different directions. CryoRead focused on how to build DNA RNA structures from the CryoEM maps, and Diff Modeler focused how to build proteins from the CryoEM maps. So first, I will briefly introduce the CryoRead pipeline. CryoRead overall idea is from the bottom to top. Since the basic component of DNA RNA is nucleotide and it includes phosphate, sugar, and base, so we use the deep learning tools to detect those information from CryoEM maps, and from there we mimic the phosphate sugar backbone to trace the phosphate backbone from the segmentation results. Then we further use deep learning to detect the base types to assign different base types to different nucleotides, and then we deposit the standard nucleotide into corresponding regions to build the full 3D structures. We have the CryoRead web server available online through the GitHub that you can clone the source code and run locally. Similar to deep learning math, we also require that you have the GPU to run it. And we also have the free server available online that you can easily run CryoRead. You can also use the QR code to scan to try later if you want. Any maps in the EMDB database that includes DNA RNA in the resolution from 0 to 5 can be properly modeled by CryoRead. And this work is also published in Nature Methods in last year, 2023. So the first step, if you go to this link, you can easily see our CryoRead job submission page. And we have one example here. You can mimic the example to prepare your results. So basically, we require the input map as well as the control level. Control level basically give a threshold to filter out the regions that you don't want to model. But if you don't know for sure the control level, you can just put 0 and our model can automatically detect the structural regions. And also you have a rough estimation of the resolution of the EM maps you should input here. And if you know the sequence information, you can provide the FAST file here. If you are not sure, you can just skip it and upload it. And after you upload your structures, you can see your results in My Jobs. If you did not registered in our website, you will be redirected to a job view page. Please bookmark the specific link, and after the results are done, you can use the specific link to access the jobs and the visualization results. So here, after the job finish, if you go to My Jobs, you'll use that specific link. You can see your model structures here, and you can also click the right top button to download the structures for local refinement or some other stuff you want to try. And to see if that agrees with the map, you can also click the Show Map to compare the structure against the map. As you can see here, we model the DNA structures from the map, and we successfully segment the proteins nearby it, and we only focus on DNA RNA structure modeling. And you can also click the isosurface button to adjust the ISO values, to adjust the contour level of the map, to see if the structure agrees well with the map. We also have the Colab platform of CryoEM. So Colab platform, similar as Genki described, it only has 2 CPUs, and its computation power is relatively limited. But the good thing for our Colab is that you can see step-by-step running, so that you can know how CryoEM is doing the structural modelings, and you can also know how we configure the environment locally. If you want to try the code locally, you can also mimic the environment configuration in our Colab. You can also directly run Colab online. So first, to run Colab, you need to log into your Google account. After you successfully log in, you can see your icon in your right top in the page. And then you simply click the connect button to connect to the local machines, the online machines that Google will automatically assign to you, which is free for 4-hour usage per day. And after that is done, you can simply click install dependencies to install all the dependencies to Google online machine. And then you can configure the map, upload the map and fast file by click the input CryoEM Map to click here to run. And similarly, you can click here to run to upload your fast files. If you choose use our also examples, you can skip this step. And after that is done, you can input all the necessary information such as contour level. If you only want to run the detection without modeling, or if you want to use the sequence or not, make sure you input all the information correctly and then click here to run to configure the information. And after that, you can run CryoEM. And after CryoEM is successfully done, you can see the information CryoEM is done here. And after all those steps, you can download the detection and PDB files locally by click the download output button here. You can also visualize the structures online. By click here, you can see the modeled atomic details of the DNA structure online. And after that, I will describe the diff modeler, which focuses on how to combine the AlphaFold to predicted single chain structures to model the protein complex from the EM map. So first, with our diffusion model, we will sharpen the CryoEM maps, which focus on the backbones of the CryoEM maps, and we will take the multiple sequence into AlphaFold to run AlphaFold to get different AlphaFold to predicted single chain structures. Then we run our previous developed tool Whisper to fit those single chain structures into different positions in the trace backbone. And then we use our algorithms to assemble those different chains together to have the full protein complex. The diff modeler web server is available online with 2 usages. The first usage is that if you already run AlphaFold 2 or you know those templates, you can directly provide the templates through the diff modeler. Also, if you are not sure, you just want us to run AlphaFold for you, you can simply provide the FASTA sequence. We will search against the AlphaFold templates and assemble the structures for you. So similar as CryoEM and deep brain mass, by accessing this link, you can run deep model. And we also provide the example here, which includes all the details. You can mimic this example to submit your own examples. So similarly, we provide the contour level and resolution and the EM map as well as a PDB zip file. If you know the templates, you can combine all the templates into a zip file. And similarly, for the zip file, you want to specify which PDB corresponds to which things. In this text file, for each line, you will write PDB file name and the chains that it corresponds to. It can correspond to multiple chains, and you only need to use the blank to split those chains. And our scripts can automatically detect that and use that information to assemble. After that information is done, similarly, you can be redirected to a link. You can also bookmark it, and if you register, you can also access the jobs under My Jobs. So after the job is done, you can visualize the results online. If you want to model locally to do some local refinement, you can also download outputs by clicking the button here. It will be in CIA format. And if you have any questions or concerns, if some structural modeling failed, you can simply click the submit for review in this page, in the visualization page, and you can give some comments here, and it will automatically send to all the web server administrator, and we will be notified. We will process the jobs to debug it as soon as possible and give feedback to you. The feedback information will also be shown in the same visualization page. If you are registered, we will also send emails to you about our debugging results. That's all. Thank you. If you have any questions, welcome to us.
Thank you so much, Dr. Wang.
Thank you.
Thank you for the information. We're so grateful. So are there questions on site, online? Questions for Dr. Wang? I don't think there is any. All right, so in the absence of any, we want to thank you so much for your time and the effort you put in to make these presentations possible. We're very, very grateful, and we hope to work together in the nearest future. Thank you so much. So at this point, we want to invite Professor Olemika for the closing remarks for today. Thank you.
Thank you very much. It's a pleasure to be here again to give a few comments at the end of this session. Straight away, I would like to thank Professor Kihara and the members of his lab, especially the other presenters, Dr. Terashi and Dr. Wang. We have been truly, truly enriched. Like I observed yesterday, we are grateful to have this. And I don't know whether it's available anywhere else in Africa for now. So we are really, really privileged. And we want to thank you immensely. We are grateful. We thank Yomi for bringing this here, and the rest of the JARIS team. We do not take this for granted, and we want to appreciate you deeply. Also to everyone who is here on site and also online, know many people have struggled through the time zones where it's not been very, it may be convenient for some, it may not be convenient for some others, as the time zones have differed. And so we want to thank you all, we salute you, we appreciate your being there. Thank you very much, and as we look forward to the final sessions of this workshop, it's my pleasure to say thank you to all of you. And we look forward to using the resources that in Professor Kihara's lab and key into some of the new techniques that we are being introduced to. We're grateful from this end. I say thank you all.
So once again, we appreciate our professors, Professor Wang in absentia, who facilitated yesterday's session, Professor Victor Chen also, Jahwe, myself, who have facilitated some sessions previously. And right now, we appreciate our Professor Kihara for coming with his team, Dr. Genki and Dr. Wang, for the wonderful and amazing presentation. Just like our prof has said, Professor Lemika, we look forward to using those resources and keying into what is happening globally, as we are also in Nigeria currently. So we would like to bring this session to a close right now and look forward to the evening session, which will be coming up, I think about 2 hours from now, which will be fully virtual. Professor Tisila Johnson and Mr. Okoyemi Waloye will be facilitating that session on virtual screening, computer-aided drug design, related stuff, molecular docking, and interest in molecular dynamic simulation. So they'll be giving us lectures and also hands-on practical on that session. So please look forward to it. Join again. That will be fully virtual. So we are closing the on-site participation from this session. So thank you very much. See you in the evening and also forever.